Hello everyone, thanks Robert for the invitation, happy to be here. It's my, I'm just back at work. I just came back also not only from Switzerland but also out of a paternity leave. So it's my getting back to work, starting with the talk. It's nice, it's good to see so many people here. I'm Mathias Soeken, I work at Microsoft, and I'm really passionate about programming quantum computers. But there are not many quantum computers. So there are some small quantum computers, but I'm interested in programming the quantum computers of the future because they promise to solve important problems that we have. So we're looking to build these quantum computers to solve things that we cannot solve today and that we don't think we can solve with classical computers in a reasonable time frame that is like less than, 6 times the age of the universe. Quantum computers can do this by breaking the complexity barrier. Now we can wait until these computers have been built and then start programming our software, but I don't think it will work like this. In the same time, while we're building the computers, we can start writing the software that runs on these computers. Because this software will not be will be very specialized software to solve very specialized problems, and it will also be probably software that runs once. Right? We want to solve a problem, we run the software, we run our program, it solves our problem, then we don't need to run it again if we have solved our problem. We may solve a different instance of the problem and so on, but if we want to solve something, we find our solution to some chemistry problem, for example, and we're done. So it's worth to spend also a significant amount of time in writing this software. And my background is in logic synthesis and design automation, where you really write software on a very, very low level. That you have to do all these kind of like bit tricks and things to write your software. So it's kind of similar here. We want to have like high-level abstractions, but also we really are thinking a lot like how do we write the software, what is the best way to do it. But how do I get some feedback about the quality of my software? I can't simulate a quantum program unless it has like a few number of qubits. I can't run the quantum program on many machines because they don't have like enough qubits for these problems. So what can I do? I can resource estimate the program. I can simulate the program as if I would run it on a future quantum computer to understand what would it take to solve this problem given some assumptions on the future. And so we call this resource estimation, and we do this to understand today what of our problems can be solved with a quantum computer and which cannot. Right? And in these problems even, which of the instances of some problems can be solved and which instances cannot. The first step is to find a quantum algorithm, proving that you beat the classical complexity of the algorithm. You're instead of like, maybe you're exponentially faster, or you're like polynomial faster. But that's not only it. So even if you show that, it may not be sufficient to run this program. It may still take like, maybe 10,000 years instead of like 10 billion years. So we didn't gain anything. So we have to like get really down to the constants, find the best implementation possible for a program, and then check how much time does it take. To understand do we achieve what we call practical quantum advantage. So what is practical quantum advantage? First, we have an advantage over classical in terms of like complexity. Where we can see, for example, in this chart, right? We could imagine there's a classical computation that maybe takes exponential time and then is exponentially faster with quantum. But then a quantum computer is also significantly slower than a classical computer. We're far away from like technological breakthroughs that have been in transistors, and also like it's just a different technology. It just doesn't run that fast. So they're slower. So the benefit of this complexity advantage is only reached after some time. So when that time hits, that's important for practical quantum advantage. And we consider this as a matter of like maybe a couple of weeks, maybe a month tops. That should be like how long it should take to run the program. Otherwise, it's not very practical. And the other thing is the problem size. Right? It could be that we achieve an advantage only in a problem size of like some really impractical problem, like a really huge instance of which there's no practical counterpart. So if these two meet, we have a reasonable problem size that describes the problem of our interest, and we can solve it in a couple of weeks. then we think it's practically on advantage. But how do we test that? We don't have a quantum computer. So we simulate that using software. We write the quantum program, and we pretend we run it on a fault-tolerant quantum computer. And we do the computations of like resource overheads that would be required to build this computer. How much time does it take? How much qubits does it take? And so on. So one more slide backing up this kind of like difference between the speed. It's just some numbers that are taken from the reference down here, where we compare like a classical chip, this is some NVIDIA GPU, and a hypothetical quantum chip, but based on some numbers from the literature. It just, and the exact numbers are not even that important, but in this case, it's just like the difference in numbers of operations that we can do on a classical computer is significantly faster, like maybe 10 orders of magnitude faster than a quantum computer. So we have to do like a lot of computation to break this kind of advantage of the classical computer. Meaning that quantum computing really pays off if we have like big compute problems rather than big data problems. Because there's also like a large difference in reading in data to a computer. So how do we do that? And essentially, so I just came, I didn't hear what's the pipeline, but essentially we're building this, we're modeling the quantum computing stack, and it's similar to how we would model a classical computer. You start somewhere with a high-level quantum programming language, because if you want to write large-scale programs, you need something to manage that. You need some kind of way to not lose focus of what you're writing. And then there are some transformations that take place in order to run on a quantum computer. We may transform it into some intermediate representation, and then into some instruction set that can be supported by the computer. Similar like we have instruction sets on a classical computer. But the difference of this instruction set of type is also very, very different, right? And classical computer instruction set is something like multiply these two registers and save it somewhere else. In the quantum computer, this is much more lower level, right? The instruction set maybe measure these kind of qubits or apply a C-node on two qubits. And that's a logical instruction set. That's a key difference to the classical computer. Then there is a microcode level that is in quantum world essentially quantum error correction that breaks down these logical operations into physical operations. Right? Each logical qubit is encoded by multiple physical qubits, and each logic operator is encoded by multiple physical operations, each coming with some measurement, some decoding phase, and error correction phase, so that we can run without getting the errors of the noise of the quantum computer and get a meaningful result in the end of the day. And then these physical instructions, they are translated to whatever is that is the physical mechanism of the qubit that we control. And in the middle, there's this quantum instruction set architecture, which is really like the maybe where the software and hardware world meets, so to say. Also, quantum error correction is also hardware, software, right? But like, there's two tasks. One task is how do I get a quantum program in representation in terms of an instruction set architecture, like just instruction sets that the computer understands. And then how do I translate these instructions to the language of the physical quantum computer? And if I do these two, then I can estimate the resources. Right? I first estimate the number of instructions, or like which instructions, and then I compute the cost of these instructions. So the error correction is really important because the noise is large from quantum computers. So just to give you a sample computation. If we take, and this is, I think, breaking 2048-bit RSA integers. So if we write down the algorithm and we take the requirements to run this algorithm in terms of logical operations, and we assume some noise, and here are some different architectures or models of architectures, like maybe something that represents trapped ions, superconducting qubits, Mariana qubits. They have like, there's microsecond or nanosecond regime, there's like the operating speeds of the gates, and then there are like different assumptions on error rates, maybe 10⁻³ or 10⁻⁴ gate error rates and readout error rates. And if you want to run these factoring algorithm with like a precision of maybe 2/3, which would give us a good result, but we can verify afterwards classically, then each logical operation should only fail with an error of like 3.5 to the power of times 10 to the power minus 16. So one can compute this, but what is the requirement for that? So we need an error less than this. And there will also be T factories, I will talk a little bit about this later, that support the execution of this algorithm. And these T factories produce T gates, and each of these have to have a quality of failing with like 7.4 times 10 to the minus 12 error in this computation. And to support this using this lower error rates that we have available on the physical quantum computer, this means we have error correction. Error correction determines the code distance, which is this column D over here. And from the distance, then we can compute what does it mean in terms of qubit count and logical time step. Just to give one example, if we, for example, take the first row, well, this would mean we need a code distance of 27. That means one logical qubit is encoded by means of 1,458 physical qubits, and an operation would take 16 milliseconds. And for the T factory that produces one high-quality T state of that error rate would require like 17,640 qubits and 163 milliseconds. But the different computers have different assumptions. Also, different applications have different numbers, right? So we will not have the same computer with the same error correction, with the same distances for every problem, but we have different ones, depending on the algorithm we run and depending on the computer we map to. And we want some software that computes that for us, so we don't want to do this ourselves. And if we do this, we can do this for applications. It's just like some more examples of these error rates that are required for some what we call practical quantum advanced applications, like this quantum dynamics, which is a simple Ising model to simulate quantum chemistry application using double factorized qubitization and factoring. So here are these applications again. So we don't think that quantum dynamics maybe is a practical application in the sense of that it solves a problem that we're like curious to solve, but it's a interesting problem of size that has at least scientific understanding. But factoring and quantum chemistry, of course, solves something that we're interested in and can solve today. So we see here these a plot where we see on the x-axis the runtime it takes in wall clock time to run the algorithm, and on the y-axis the number of physical qubits. It's a bit maybe hidden, but it's like 10,000, 100,000, 1 million in the middle, and 10 million, 100 million on the top in log scale. And then each of these applications has 6 different data points depending on the assumptions on the hardware that we make. But these are just some presets. One can make other assumptions, right? And then we see like where does it land. And the most important message for me is that we can, with these assumptions, and if this turns out to be true, that we can build these machines and we can achieve practical quantum advantage to solve like factoring or quantum chemistry. Right? Chemistry is within weeks, between weeks and months, factoring less than days, but requires more qubits. So that's good news. Quantum dynamics is an interesting example because it also shows something that is hidden basically in the stack. When you go from a high-level application down to the machine, you have so many different possibilities to run your algorithm. Even if you don't, so you have already so many ways to program your application, but even if you have the same program, you have so many different ways to execute on your quantum machine. You can use different error correction schemes, you can use different mapping and layout and different T-factory configurations, so there's so many different possibilities. Here's just one example of choosing like 2 different compilation styles. We saw in the purple one on the left that this was running very, very fast, but it takes a lot of qubits. So it's less than seconds, but it takes a lot of qubits. So it's okay if it runs slower. So if we manage to make it run slower, we can save some qubits, okay. So we saw in the resource estimator, and I saw a sample for that this algorithm required a lot of T gates and a lot of T factories. So most of the algorithm were just producing T states. So let's produce fewer T states over longer time. So the algorithm runs slower, but then we can reduce number of qubits because we don't need so many qubits for T factories. And I showed a sample for that. So there are like space-time trade, not only like two space-time trade-offs, but there's like a huge space of space-time trade-offs resulting on decisions on every step of the stack. So before I go deeper and like show how we do the resource estimation, I show a demo. So this resource estimator is freely available in Azure Quantum. That's the Microsoft Quantum Programming Platform in Azure. So one creates an Azure account and then creates an Azure Quantum Workspace. And then you get this sample gallery. And there's like resource estimation. And then there are different samples to start from. So I just pick some of these. So these are the samples that generate the numbers that were shown on the slide for these three applications: quantum dynamics, quantum chemistry, and factoring. So if I go into this, maybe I start with the chemistry one. So just running all the cells now. So this is a Jupyter notebook. So you can, for example, access this in Python, but you can also do this in other languages. You can insert your quantum program in different kind of languages. So in here, the resource estimator reads QIR, which is intermediate representation for quantum programs, but many languages like Qiskit or Q# or others translate to QIR. In fact, QIR is LLVM. So if you know like LLVM, you may know that C++ or Rust also translates to LLVM. So also this, in that way, like Rust or C++ would also be quantum programming language you can use with resource estimator. In fact, this is what we did here. This is applying the double factorized chemistry application in which you can provide your own Hamiltonian. So if you have an Hamiltonian that is in some chemistry format called FCI-dump that you can describe, and if you have a file for that, and there are some samples here provided by us, but you can bring your own like Hamiltonian, you can give it as input to the algorithm, and then the algorithm does all the pre-processing, or like having factorization and so on. And in fact, this is like a Rust program. So we send a Rust program that's compiled to LLVM and then execute like this. We can specify some parameters. So in this case, we specify the default parameters for the different 6 quantum computers that I have like shown before. So, but one can specify many things, but not only like these samples, but you can define like operating speed, error rates for measurement, and so on individually. Then we run the result, we get a table like this. Right? This shows these 6 data points that were on the slide for quantum dynamics, which shows like number of logical qubits. This is like a summary view, so that there are more data, but this is some view on that, like logical qubits, logical depths, T states, co-distance, T factories, and the fraction and so on. And then the time that is in fact less than a month for a few cases. We can also look at the detailed resource estimates. So there's these are like runtime, physical qubits, and a metric called RQOPs. Then there is the breakdown of resource estimates, where like how much do I need for, let's take for example, take a look. So we have 1,340,000 physical qubits. But where do they come from, right? So how did that happen? Then I can see that there is 1.1 million for the algorithm and 232,000 algorithms for the T factory. So why do I need 1.1 million qubits? Because this is the product of having 2,844 logical qubits, each of which having 388 physical qubits. So why do I have like 388 physical qubits? I can look at my logical qubit parameter. So I see there's a co-distance of 9 based on my logical error rate. And then I have the formulas that compute the number of qubits. For example, here it's 4 times co-distance squared plus 8 times co-distance minus 1 and so on. And then that computes the numbers. So I don't go to all of this now. But what I want to show is like first, you're going to get a lot of numbers. So if you're an expert in fault-tolerant quantum computing error correction, there's a lot of numbers there to work with. But you don't need all these numbers, right? You just want to give a lot of numbers to work with, to do something interesting, for example, in post-processing. But also, when you're new to fault-tolerant quantum computing and you want to learn more, right? Then we have the description text on the right, which explains like how has this number been computed based on other numbers, and then there's like a link to this other cell, and you can like, really do the derivation completely. How these numbers have been happened? They are not coming out of the sky, so you can see like where they come from, up to like the number of logical operations in your input program. I think that's here before mapping it to a layout. And maybe the other ones I don't run now, but I just show like how they have been computed already. This is an example for this quantum dynamics. And here what's interesting to point out first that you have the whole implementation of this algorithm in Q#, also part of this notebook. So it's embedded in this Python notebook. There's Q# code for the whole application, so you can also change it and see how changes affect the resource estimates, or trying different optimizations, for example. We specify input parameters for this instance, and then also different parameters for the hardware. And then we get, again, a number table. And what I just said, where we saw that there's a lot of like T-factories in this algorithm. They run very fast, but they need a lot of space for T-factories. We also see this in these charts that one can print to kind of like really zoom in onto like what takes my space. So I see like a bit of space for running the algorithm, but a lot of space to produce T-states to be consumed by the algorithm, with the highlight numbers that contribute to the space. And then one can, you can also show the time of how this runs. But you can also perform some optimizations. For example, here's a constraint that we want to like run the algorithm like 10 times slower. So essentially we perform 9 no operations for every logical operations. By doing this, we have more time to produce T-states, so we need fewer T-factories, and that shows then also in the numbers, right? So now we're like fewer qubits for more runtime, and we see the T-factory fraction goes now maybe more towards 50%, which seems like a good trade-off. But that is also dependent on the application and the instance that you use. But that's why it's an analysis tool, and I think that's why also Jupyter Notebooks fit very well to like really work with your problem and see what happens if you change different parameters. Finally, I want to also show the factoring algorithm. That's these are 2048-bit integer factorization on a paper by Gidney and Hastad. And what we did here is a different way to implement it. This is the whole implementation, but it's just like a summary, basically. So one can also perform physical estimation just by giving logical estimates. So if one has a paper that says, okay, I can do this with that many T-gates, that many like rotations, that many Toffel gates, and so on, one can just specify these numbers. This is more a quantum program, but this can serve as input to also perform physical resource estimation. But this may be a good starting point, just to start with some logical counts to see what happens, and then maybe work on these logical counts. You can even do like assumptions, like what if I could bring the number of qubits, if I can halve them, right? If I don't need like 12,000, but I need only 6,000. I may have a hunch how to do this, but I don't know yet exactly how this will work out. Before I start working on this, I could like just try it out and see what would the effect be on the resources, and if it's like really impactful, then I say, okay, this is really worth to go that route, or like to decide between different routes. So in that way, it's also like a valuable research tool. And here are the numbers again. So going back to the presentation, I want to show a little bit more what's going on in the hood, how we do this. So you give us input, application input, your program, for example, Q# program, skip program, a model about your qubit assumptions, a model about your quantum recursion code assumptions. And then first step is that we translate the program into an intermediate representation, which we can think of like a quantum circuit. And then we normalize it to a normalized form, for which we have an easy way of performing layout. And then we take this normalized form and mapping it to an architecture that gets input from like our qubit models and quantum encode schemes, right? So these are logical qubits, and then the size and the duration will be based on the input parameters of the hardware. And then on that model, we can derive like the numbers that I've shown in this table, or we can get a lot of data and make plots and work with the results. So we go through every step. So how do we get a quantum circuit? A quantum circuit is like a trace of a quantum program. Right? If we just think we are a program counter now, and we are like going through the program and allocating some qubits, is a Y in the quantum circuit, allocating some more qubits, entering a for loop, applying a T-gate, applying some operation. This is like swap registers that can only be done with Clifford operations, so I just abbreviated this like C1, some Clifford operation. Applying another T-gate, so this is like Q-sharp syntax for like a conjugation application, right? You have often in quantum algorithms do something and do something in the middle, and then do the first thing adjoint or in reverse order. So it's good to have some syntax for that, and then maybe measure some qubit, and then do this again for in total 3 times, right? So this would be the quantum circuit representation of that quantum program. In reality, it's not that long, right? So the loops and so on will be contained in the representation. But if we like execute it, we can think that the quantum program is like the execution of our input. Now, we will have to map it to hardware. And there are many different ways to do layout. We're doing something called parallel synthesis sequential Pauli computation, in which we remove the Clifford operations from the input circuit by translating the non-Clifford operations into multi-qubit Pauli measurements. And that works in some way like this, that if we have like the Clifford in the beginning, C1, we can move it over the T-gate, and then it becomes some multi-qubit Pauli measurement. This is a Clifford operation on these 6 qubits, but it requires a T-state. It has to be produced, one T-state, that has to be produced by some T-factory. Then we can move it over a measurement. This just creates a multi-qubit Pauli measurement. These multi-qubit Pauli measurement interacts with potentially all qubits and has different bases on the qubits, maybe I, X, Y, Z. And we move it further, right? And then if a Clifford meets another Clifford, they just become a, I don't know, maybe bigger Clifford. So they become a different Clifford, and then we can continue until the Clifford is like out of the circuit. What happens then? We can just disappear. Essentially, what we can do, we can think of like the Clifford can be applied as a post-process after the measurement, and Clifford simulation is classically efficient. So we don't even do this because we want to do resource estimation. And the first T is very alone, but we can also think of it as a multi-qubit Pauli measurement that is fed by a T-state. So now it's a very uniform representation of the quantum program, just multi-qubit Pauli measurements. Some of them require a T-state that has to be produced by a T-factory, some of which don't. And that's essentially the quantum ISI in this resource estimation tool. Every operation is a single instruction in the instruction set architecture. Now this can be mapped. Because it's just one instruction, it's easy to map it. We have in purple the logical qubits for the algorithm. These are like the 6 qubits in the circuit. And then there's some padding needed. This is in order of like 2 times the number of qubits plus some square constant. So you pad these qubits with these gray ones that are helper qubits to do the layout, but it's essentially like doubled. And then we have the space in yellow for T-factories. And T-factories are just there to produce T-states. And they produce T-states, and then the instruction can take this T-state. And if we need many T-states, we just produce more T-states by having multiple T-factory copies. And we can run T-factories as long as the algorithm runs. So the algorithm determines the runtime. We can make it a bit longer, and then the T-factories are just producing T-states as much as they need. Then, once we have mapped this, right, we have to understand what does it take to build a logical qubit based on error correction, and there are just different schemes that one can use in the tool predefined are surface codes and hustling hard codes, but one can change the assumptions for similar codes. And they have like a trade-off in terms of like noise, speed, and number of qubits. And the last one is the T factories. They produce T states, and essentially what happens is that you have a physical computer that can produce a noisy, low-quality T state, maybe 10 to the minus 3. But now you need a T state of quality 10 to the minus 12. So you take a lot of like noisier T states, starting with the physical ones, taking a lot of them, and you distill them in circuits that are called distillation units, and produce higher quality T states. So maybe, for example, we have these 15 times 15 physical T states that are produced by physical T gates. And then maybe 15 T states can be used to produce one higher quality T state. Right now we have like this one in the middle, and then we can take these. So now we have new T states, higher quality, maybe, I don't know, 10 to the minus 7. But we want to go to 10 to the minus 12. So we're not there yet. We can just do another round of this. So we can repeat this process of distillation unit, again taking these 15 qubits, maybe we have to like expand them to a different code distance, and then merge them again together. 15 becomes 1, and then this is like, out of this 15 times 15 initial T states, we have now 1. And that is maybe the sufficient quality, and then we can use this one. And that also happens. And that is also often taking a large amount of the computation, where trade-offs become very important. It just summarizes the tool. So we provide a lot of input or possibilities to put input in the tool, like application input can be Q#, Qiskit, like LLVM. But you can also bring your own programs. So we have some applications there, some samples, but you can bring your own programs. And then we have a Q# compiler that translates Q# into Qiskit, a compiler that translates Qiskit into QIR, and you can also have your own compiler that translates into QIR to run resource estimation. Resource estimator then takes the QIR code, and then there are some built-in QEC schemes and qubit parameter settings, and you can bring your own and change these settings. And analysis and visualization tools, like for example the tables, summary tables, diagrams, just very new, is also like profiling capabilities, so you can see the resource estimates of the intermediate operations in your program. So not only see the total estimates, but also like dive deeper into like what contributes to this resource estimates. Like maybe what is a bottleneck operation to understand a focus on where to optimize next. And if you want to get started or like continue learning about resource estimation, you find everything in like quantum.microsoft.com. And I'm gonna show already like how this looks like. So there's this is the web page. This is quantum.microsoft.com, and here you can learn a lot about like not only resource estimation, but about the whole quantum program from Microsoft, including quantum software and the quantum machine. Also, what's nice, you can also do some coding here. This is Q# on the Microsoft web page, but you can now use Q# in the browser. So you can take a program, run it. So there has been a complete re-implementation of Q#. There's also a nice blog post about it, and it's like now 100 times faster, 100 times smaller, and it runs in the browser. So they've changed the complete implementation of Q#. And it's now very fast. You can run it here. It's coupled with, if you log into this web page with your Microsoft account, but that's just a normal Microsoft account, you can also use Copilot in helping you writing quantum programs, because it's still very daunting to write quantum programs. And sometimes Copilot has some good suggestions. But it's like, like every Copilot, right? We get a suggestion, we take the suggestion, we try running it, maybe there's some things we have to change. So I'm just asking the default question, but you can really try all your own questions, all your own things that you would like to see, how the code looks for that. And then it takes a while. Here's the answer to this. I don't even read it now, I just run it. But it seems to 60-50. Maybe I have to increase the number of shots. But it looks like 50-50, almost. at least when I look at the code, and it seems to do the right thing. If I wouldn't know like exactly if it did the right thing, I can also ask Copilot to just take the code and explain it back to me. But you can also change your code and maybe ask Copilot to explain your code that you wrote, or maybe after some time. And I don't know what I wrote, maybe Copilot knows. So it's a good team to do quantum programming on this webpage. You can, maybe I'll wait and see what Copilot says about the code that is suggested. For those who haven't seen Q#, right, it's like a language where you describe quantum operations. You have classical constructs like for loops, if statements, function calls, and so on, like in a mathematical library. And then you can call gates, but you have some. You bring like high-level abstraction by having operations that cause up operations, by having some constructs that help you writing, mimicking typical quantum computing patterns, and support like dump machine that gives you the intermediate state as long as you can simulate it. And then there's an explanation from Copilot in different steps, like what happens, what does every operation do, and so on. If you want to learn Q#, you can also use the quantum katas, and they are also now part of this webpage. These are like, it's documentation material about Q#, not only about Q#, it's also teaching about quantum computing and the quantum computing basics, right, like qubit, single qubit gates, multi-qubit systems. And then if you go in here, maybe I take this one, we can unfold the different chapters. There's a lot of like learning material to learn about this. And every now and then, and especially in the later chapters, more often, you get also like an exercise. So it has some code here, for example, right? So it wants you to apply a Y gate. It's not a very challenging task right now, but like the deeper you go into the material, the more difficult also the programming task gets. So I should apply a Y gate to the qubit Q. Any idea how that could look like? I could also ask Copilot. I don't know. But probably all new. Just asking YQ, then I can run it. And this was a successful exercise. I get correct, I can track my progress, and I can also throw the solution or like interact with Copilot in this experience to learn more about that. Yeah? And now we have more time for questions. Thank you, everyone.